Can't read the notes on it. There we go. I've got a question. Number 5. All right. I'll take it just a second. Okay. Good morning. Welcome to class. I will tell you this much. I've been grading exams. It takes forever to grade take-home exams. It takes forever, even longer. Forever more, forever plus. I don't know. Anyway, it takes even longer to grade take-home exams with that I give out the problems because they're nasty and they're electronic, and anyway, it's just a pain. So I'm not done yet, but I am making progress on them. This much I can say is it seems to me that you guys are actually understanding some of the stuff. You know, there was at least some semblance of understanding on pretty much everybody on the set jump problem. It's refreshing because I so often encounter problems where the answer is a big old question mark, and if I'm lucky, sometimes two. So it seems obviously there's things that I can pick at, but so far I'm not going to have to curb the test like radically. Well, I did start grading the third problem. Well, the third one, the context switch optimization. There's more smorgasbord answer on that one, but at least I think that we're communicating at least that much. I think that some of the stuff that I'm saying you guys are getting, and some of the stuff that you guys are getting, I might be able to take credit for. But anyway, so it's going well. We'll put it that way. I hope to have them done. Depending on how things go today, maybe today, it might be tomorrow, but I'm going to try to get them done here pretty quick. So we'll see how it goes. Anyway, questions? Brad.
How would you use the process name that we assign from the command prompt? You know how in previous labs we used a number to identify a process? Are we supposed to replace that with the name, or are we supposed to add the name to the process struct?
Okay, so the question is, what's the purpose of the name that you send in on the command prompt? How do we make use of that name? Are we supposed to no longer have an integer ID for a process? What do we do with that string that you supply in the create process command? So the whole idea here is, so let me give you the long answer to the short question. The idea is you've got a user that's effectively telling your system to fork off processes. When that user says, I want to know what's going on with process number 2. Which one's process 2? How does the user know which one's process 2? So the user doesn't understand what the internal workings are of your system, especially when your system gets to decide which priority a process gets. Now, sure, the system could respond to a create process command and say, okay, yeah, I created a process, and the process I created is number 2. And that way the user could then keep track of which one is number 2. But we want to let the user keep track of which process is which in terms that the user says. So I want to create a process Fred. And then I want to later figure out what's the status of process Fred. The system internally can keep track of which process is actually Fred based on a number. So yes, you can still keep track of a process ID based on a number. But you should also have associated with that process the string. And how you do that is you store the string in the process data structure, and you reference it as part of the process data structure.
So if you want to show process Fred, does that mean you have to loop through all the processes and check their structures to see if Fred is their name?
So if you want to show process Fred, how do you go about doing that? The answer to that is one approach is looping through all the created processes, or through all the processes, all the 64 slots in your process array, figure out which ones have been allocated, and for those that have been allocated, does their string match the string that you're after? That is one way to do it. Another way of doing it... Okay, so the question then becomes, is there a problem with non-determinism? That's a very good question to ask. You're thinking in the right directions here. Yes, that is very much non-deterministic, and no, we don't care. The reason why is because it's running in your UI. So it's not part of your operating system, it's part of your UI process. And it's the user interface process itself, and that can be non-deterministic. I mean, it calls printf, it calls fgetf. Those are all non-deterministic. So you can tolerate non-determinism in the UI process, not in your operating system, not in your real-time tasks. Okay? One thing to watch out for, okay, so there's a variety of bugs that can come into your system. As we talk about things like what's going on in your labs, I will point out where students have often made errors and where it's come back to haunt them. Particularly with the process name. If you allocate as part of your process data structure a pointer to a character, and then when you are inside your proc create and you pass in as a parameter a pointer to a character that points to the string that the user provided, and then all you do is you point the pointer in your process data structure at whatever the parameter points to and call it good, the problem is that string that you are passing in as a parameter to your proc create, it needs to be copied. You can't just point a pointer inside the process data structure to another field. You actually have to declare a character array as part of your process data structure and copy the contents of the string you pass in as a parameter to proc create into the space that you have allocated inside your process data structure to hold the string. If you just have a pointer that points to a string and you pass in that string will be part of maybe your buffer or someplace else. It won't be allocated space, and it'll end up getting overwritten. So the problem is you will either have a dangling reference if you don't allocate space in your process data structure to hold the string. It'll either be a dangling reference, or it'll get overwritten depending on how you're doing your parsing of your command line that you get in. Alternatively, you could malloc some space to hold the string, but I've told you to be careful with malloc. Now, from what Rohit informs me, you all are in a panic about malloc now. You don't need to panic about malloc. Okay, try to avoid it. Very rare are the situations to where I've encountered a malloc doing weird things that caused me to advise students to get rid of all the mallocs. And I would suggest that until you, perhaps you've already done this, but until you get into a situation to where there is absolutely no other explanation possible for what my weird behavior is, then start eliminating mallocs. But for the time being, you're probably, the one area where you can't malloc is your stacks. And if you have malloced your stacks, you've found out pretty quickly why you can't, because the moment you swap a process in, you're going to get a heap stack collision. So you can't malloc your stacks. But I wouldn't be so panicked about malloc for all the rest of the stuff unless something breaks. It's okay to malloc. But if something's really broken and you can't explain it any other way, then as a last-ditch effort, start considering allocating your own stuff outside of malloc. Okay.
So the user's going to create instances that are going to have unique names. Aren't we just making, like you gave us the a process function, so are we making instances of that process function?
Okay, so the question is, the user is going to be creating processes. All of them will have different names. I've given out code for the test process in the lab write-up that has that loop in there where a process grabs its own semaphore and then does some work. It calls it, what did I call it, delay? Call it delay function. And then it goes up and grabs its own semaphore, and it just repeats that over and over again. That code has been written so that all the real-time processes that your user invokes by calling create process, all of them should use that same code. Okay? The reason why is because it's sufficient. You don't need to do anything else inside your process. You can create different implementations, but the problem is if the user can decide what processes he's creating, he doesn't get to decide what code implements those processes. Simply because what's he going to do? Type in C code on the command prompt, and then you dynamically take the C code down, and then you compile it at runtime? We don't have a cross-compiler, or we don't have a native compiler for the ARM. You can go ahead and try to do that if you want to, but that's a mess. Yeah, extra credit. I would recommend getting Lab9 working first. So the user doesn't get to decide what the process implementation is. All of the processes in Lab 8 share the same implementation except for the UI. The UI sits at slot 63 as your lowest priority process. When you're doing your utilization calculations, you don't count process 63 as part of your utilization calculations. The reason why is because it's not a real-time task. It just sits there and takes all the extra CPU time that everybody else isn't using. Everything else, the only processes you count as part of your utilization analysis is the processes that have been created with create process, with the command line. Okay? Does that answer the question? Okay. Other questions?
Do we need to keep an array of the processes period so we can use them to calculate its processes met its deadline?
Okay, so the question is, do we need to keep track of an array of process periods so we can figure out whether or not a process has met its deadline? Or if it's time to re-release it. Right. That's the same question in Lab 8. Okay? So, effectively, yes. Technically, no. You have to keep track of every process's period and how long it is until its period's up to where it's time to release it again. The way that I've done that is I've just added another couple fields in the process data structure. And so in your in your timer interrupt, what you would do is you would have before you call schedule next process inside your timer interrupt, you call another function that's going to check your processes for releasing them. And so you'd iterate through all your processes, and you'd check to see if slot number I is equal to null. If it's equal to null, you just go on. If it's not equal to null, then that slot represents an allocated process. It's a pointer to a process. You grab the field inside that process data structure that says how long until you are supposed to be released again. And if that time is now, then you release it. Otherwise, don't release it and go on to the next one. Okay? This business of checking to see whether or not it's time to release a process can be done one of two ways. You can keep a counter that says that you decrement every time you have a pit. So inside the process data structure, you would just decrement its counter, and when that counter gets to 0, you release the process and reset the counter to a value that's equal to its period in units of timer ticks. Or alternatively, when you release a process, you can calculate what will the timer tick be at the time where I'm supposed to release the process the next time. So if the timer tick currently is 598, and this process has a 40-tick timer period, you would set the counter to 598 plus 40. And what is that? 500. Great. Why did I give nice round numbers? 638. Anyway, so at 638, you would just, so you'd have a bunch of timer ticks, 40 timer ticks until it's time to release the process again. When the timer tick is equal to 638, you're going to say, is this process's period counter equal to the current time? If it's equal to the current time, release the process. Okay? So you loop through all of your process data structures. You loop through all of the processes pointed to in your all processes array. Every pit. Again, when you get to Lab 9 and you're doing dynamic priority assignment, this is the array of process pointers that's indexed by static priority, not by dynamic priority. Okay? So now it begs the question, what does it mean to release a process? How do you release a process? You do a V on its semaphore. Not really. If you're doing a V on its semaphore, you're just calling the regular old V, you've got a bug. The reason why is, let's suppose you've got 10 processes all created, and let's suppose that 2 of them on the current timer tick are ready to be released. If you're looping through this array and you find the first one that's ready to be released and you call V on that one's semaphore, what does V do? It'll it will move that process from the block queue to the ready queue, calling move block to ready, and then call the scheduler, which let's suppose that the scheduler determines that this process you just released has a higher priority than the process that's currently running. What will happen next? You'll context switch. Or in other words, you'll stop doing what you're doing now, and you'll swap over and start running the released process. What did you not do? Your second process that you're supposed to be released didn't get released. When will he get released? Next time you run your timer tick. So you've lost a tick. So in other words, now you've got less time. And what happens if, for some odd reason, you're releasing processes in backward priority order? So you start at the lowest priority processes and go on up. Well, what if that process that you didn't release has higher priority and should have gotten the CPU right now? Bad, bad, bad. So what you need is a different implementation of V. So when you release a process, you need to have a special V that you call from your interrupt, which does not invoke the scheduler. All that it does is move a process to the ready queue. Okay? So then after you've checked all of your processes and released every one that are supposed to be released, at the end of that loop, then you call your scheduler. And your scheduler will see, of all the processes that were ready before and all the processes that I just released, who's the highest priority? Let me run that guy. Okay? Giving you away all the answers today. Should your UI process have a semaphore? Should your UI process ever not want the CPU? So your UI process should always want the CPU. It should always be at least ready, if not running. Maybe. What's the purpose of a semaphore? So we have two purposes that we've been using semaphores for. So these real-time processes that we have in Lab 8, we have the first purpose of the semaphore in there is to block the process, to take it out of contention for the CPU. We want to make it wait for the CPU. In Lab 7, when we were protecting printf to keep two processes from lacking each other's printf, we were protecting a shared critical region. So you use semaphores to protect the critical region. You also use semaphores to keep a process from contending for the CPU when you don't want it to contend for the CPU. Okay? So let's pick each of these purposes and figure out if the UI process fits either of these criteria. Okay? So should the UI process ever attempt to take itself out of contention for the CPU? Should it ever block itself? If the UI has nothing else to do, what should it be doing? Computing. What will it be doing with the compute time that it's competing for? What should it be doing? If it's got nothing else to do, what should it be doing? Waiting for input from where? Well, how's the user going to send data to it? Serial port, right? What is the user doing? So when you call, how do you get data from the serial port? What function do you call? You remember? Term function is what you call on the host side. We're talking the target side. You call the read function. Where's the read function implemented? Syscalls.c. What does it do? It pulls the serial port. It's got a for loop that says, wait until status bit says that there's a word there. And as soon as there's a word there, read the data register and give me the data word that's sitting there available and copy it into the buffer. Then do it again and keep doing that until I've gotten as many bytes as the user's requested. Okay? So, but what you have to realize is it's sitting there in a tight while loop polling a status bit. It spends by far the vast majority of its time polling the status bit of the serial port status register. Okay? So it just sits there and polls that the whole time. So the time that we steal away from the user interface is the time corresponding to that polling time, where it screensavers. Okay, so we're spending a whole lot of time polling that bit. Well, what happens if we don't poll the bit? If we just look at it and then go and do something else, and look at it and go do something else, and look at it and go do something else, but just as long as we sample it frequently enough that we never miss data. Do we need to poll that bit all the time? What happens if we don't poll it often enough? Then you're going to have a word arrive and get put into the data register, and then if you don't figure out that there's data available until it's, by the time that another word arrives, it'll overwrite your last one. So you've got the time that it takes to transfer one byte in order to sample that, get the data out. So as soon as you sample that, get the data out, then you've got maximum the time that it takes for it to transfer a whole other word before you can, that's the maximum amount of time until you start to potentially lose data. Okay? So how much time is that? How much, you know what the baud rate is. So worst case. So in the worst, so it depends on how much information the user's sending, yes, but in the worst case, the user's sending data all the time. So if we just assume there's a constant stream of data, how much slack do we have? How much time do we have available to steal away from the UI before we lose data? What's our baud rate? Come on, Mitch, you hacked your own serial port. You ought to know this one. Yeah, so it's a little bit over 100,000. Isn't it like a... But what does that mean? What is that? 115,000. What does that mean? That's a baud rate. Okay? How much data do we send? So a baud rate is, what's the units of baud? What is it? What are we transferring with baud? What does the baud tell us? Aren't I good? Wasn't I good? Steer it right back to the lecture notes that I've been showing the whole time. Okay, baud rate says how many bits are you transferring per unit time? Not how many data bits, but how many total bits are you transferring per unit time. Take the inverse of baud. That says how much time does it take to transfer a bit. Okay? How many bits do we transfer per data word? You transfer one start bit, 8 data bits, 1 stop bit. That's a total of 10 bits. Okay? So you have 10 bit periods. That's the total time that it takes to transfer one word. So you have to check your serial port at least that often. Okay? If you're not able to check it at least that often, you run the potential of missing data. It does not guarantee that you will miss data because it's up to the user on how often they're sending data. But potentially you will miss data. So what you do is you take 115,000, take the inverse of that. That tells you how much time per bit you're getting. And you take that times 10. That tells you how much time you have in units of seconds. So it'll be some fractional unit of seconds that tells you how much time do you have to, that gives you some sense, if you were to calculate a period for your UI, that would be the period for your UI. You're not going to set the period for the UI because what you're going to say is if I'm utilizing my processor on my board for doing real-time tasks, that's more important, and I'm okay if I occasionally lose data. So the responsiveness and the ability to send a prompt up and to receive data appropriately, we will say that takes a back seat to making sure that our real-time tasks run and meet their deadlines. So as you run your Lab 8 code and as you create more and more processes and as you try to increase the utilization of the CPU to the point to where you will miss a deadline, you're going to get to the point to where when you type in commands, you're not going to be able to type them in. It won't receive the commands. It won't respond to your commands. And that's simply because your UI isn't getting swapped in frequently enough to receive the data on the serial port. Does that make sense? So, and that's okay. Just as long as the only reason why you're missing data on the serial port is because your CPU is busy running your real-time tasks. If you can't get data onto your CPU even when you're not running real-time tasks, that's a problem. Okay? So you are going to sacrifice the responsiveness of the UI and the correctness of the UI in favor of doing your real-time tasks. Other questions? Comments? Keep asking me stuff. I'll keep giving you good stuff about the lab. But if y'all are feeling comfortable with it, then we're good to go. Tony, you had a question earlier. What did you want to ask?
That wasn't about the lab.
Okay.
And we're in lab. We measure like we measure like how long it takes to do context switch and how long he does the things. But we've always got, when we're doing this, we've always got stuff inside that like print statement like this. You have to put the timer and then call the timer and things. I mean, if you wanted a really, really accurate amount of time that it takes to run context switch, how would you calculate that? Would you have to do it just by like counting cycles and like instructions?
Okay, so the question is, we do a whole lot of shenanigans, and I've asked you multiple times to measure how long the scheduler overhead is and the context switch time, and how do you figure out exactly how much that is? I mean, if you're inserting time measurement statements, you're perturbing the measurement, especially on a context switch. If you put a time it is before your context switch and tell me what time it is after your context switch, well, arguably your timer resolution isn't fine enough to even distinguish between the start and stop time of your context switch. Maybe it is, but how do you actually, in a hyper-accurate way, measure the performance of your context switch? See, the issue with that is our processor has a cache. It has an instruction cache and it has a data cache. And you are pushing and popping data in context switch, which hits the data cache. You are also fetching instructions, which hits the instruction cache. So the performance is going to be based on how many cache misses do you have, as well as how many instructions are in there. So you could run an instruction simulator that would, if you had a cycle-accurate simulator for the ARM, you could step through the instructions inside your processor. That cycle-accurate simulator would have to factor in what's the state of the cache. And in order to factor in what's the state of the cache, it would have to run all of your program up to the point where you run context switch, and it would be able to tell you at this time you run context switch, how much time does it take. The next time you run context switch, it would not necessarily be the same number. This is why in real-time systems where you are paranoid, hard real-time systems where you're paranoid about exact how long does something take, you do not run your code on a processor with a cache. Because a cache will speed up the average execution time of your program. It does a very good job of that. But it is not deterministic. So it will not predictably improve the performance. Texas Instruments DSP chips have caches on board, and they're small L1 cache, but their L2 cache is actually configurable. So you can configure it in different chunks to say, I want half of this to be a cache that's an L2 cache for my data cache. I want the other half to be a scratchpad memory. And that scratchpad memory acts like an internal RAM that you can access yourself that has a much lower latency than going off chip. You can configure that in different chunks, so if you're doing a hard real-time task with that, what you'd do is configure the whole thing to be scratchpad and not use it as L2. And that way, if you have important code that has to run deterministically like your context switch, you would load that code into the internal memory and maybe a portion of its stack or something like that. Maybe run the IRQ stack out of the internal memory. Something along those lines. So, yeah, Derek.
You said with the delay function, we need to be pretty accurate with it, right?
So with the delay, so here's the deal. When I say accurate, I'm assuming that you're taking average case behavior, which kind of nullifies out the differences of the impact of the cache. You don't have to worry about what is your cache doing. I mean, it would be a really cool class to have you guys all go through computer architecture and real-time systems, and when we're done, now we sit down and figure out all the impact of the low-level architectural details. But how do you deal with the delay function and make it be highly, highly accurate? All that I'm saying with the delay function is you just measure how long it takes. You declare a volatile integer, and then you have a for loop that counts up from 0 up to some number. And you got to figure out how much time it takes to go from 0 to some number. So you read a timer at the beginning of that loop, and you read a timer at the end of the loop. and you make the sum number big enough so that it takes a long enough time that you can measure it accurately. So you want it to be more than one timer tick, more than two timer ticks, but thousands of timer ticks. And then you divide how many iterations you ran by how much time it takes, and that tells you that gives you an estimate. You just assume a linear relationship by saying, okay, if I know how much time per integer count it is, then I can nail down how much to count by. Okay? And that is sufficiently accurate. What bugs have you guys encountered in the lab? I know the biggest bug is invalid user IQ. I know that part, but anyway. Did bugs with FGetS? Did you have to? Yeah, FGetS doesn't work. You have to use the myFGetS from Lab 3. Like I already gave you out. Sorry. Mitch?
When it dies and you just get the string of garbage characters, it just stops. Is that usually a segmentation fault or what?
Okay, so when your program dies and you get that string of characters and it looks like it's got some dollar signs in it, and the string of characters maybe a third of the screen wide, and it's got some colons in it and all that, that is Red Boot trying to hook up to GDB. So Red Boot has code built into it to interact with GDB. That's a feature we're not using. But what that is that's code that as soon as Red Boot, after it's done doing what it's doing, and it doesn't have anything else to do, it says, okay, now it's time to hook up to GDB. So it outputs a string that's meant to go out the serial port and go up to your PC, and theoretically you would have GDB running on your PC, which would recognize that sequence of characters, and then it would be able to allow GDB to remotely debug your system. Why that comes is because main returned, or somebody called exit. Or, alternatively, you've had some exception that the processor caught, and that led to somebody calling exit and caused you to run to exit. So if you have, well, okay, it's not going to be a segmentation fault because our memory manager is configured to support memory access in real mode. But if you have an invalid instruction or you jump to some weird place in memory, if you access, well, maybe there is a segmentation fault. So if you access some region that isn't in RAM, that maybe the memory manager is configured to not support. I'm not sure exactly what our memory manager is configured at right now because the Technologic Systems guys wouldn't tell me. So they have the memory manager configured already. We could go through and reconfigure it. That wouldn't be a problem. But they wouldn't tell me exactly what the memory manager is configured to do, other than RAM is configured to start at address 0 up through address 32 megabytes.
So if that say on a context switch, calling context switch, is that how we ran over our stack?
So if you called a context switch and because of the context switch you got the little garbage stuff, yeah, you're probably jumping to some place that doesn't make sense. I would blame the address that's saved on your stack in a link register slot. Like a lot of what you guys are doing on the proc delete on your exams, that all kinds of garbage jumping locations. Anyway. No, that was everybody. And by the way, Mitch, your argument about why you can call proc delete and schedule next process, if your process that you swap in the very first time, when you call start scheduler, if that one returns, then you're going to crash.
Okay.
I knew I'd figure my way out of that one. Other questions? This is good. I hope this is helping and give you good 2 bits on the lab. What other bugs have you guys had? Because this is really helpful when you guys talk about the bugs that you've had and the things that you've seen. If I can perhaps explain them, it might help everybody else when they're debugging their stuff. And since Rohit's very good at talking you guys through bugs, you guys don't come and bug me too much, and so I don't get a good feel for what you're struggling with. So we had the little issue with Garrett's code yesterday about returning FIFO. You're still having problems. All right, don't talk to me.
Cooperative, and that's preempted.
Yeah, if you're having the random bug, which is your code's just doing something you just can't explain, first step is try to eliminate the interrupt. Try to get it to behave cooperatively. And the way you do this is you either disable the interrupt completely or make your timer interrupt have a very long period. And then try to get your bug to manifest itself with just doing cooperative scheduling. That'll simplify things tremendously. And Jonathan says, make sure any strings are null terminated. That was another thing that we found, is that if you're using strncpy, just realize that does not tack on a null terminator unless the count that you're passing is smaller than is bigger than what your source string is. Make sure your strings have a null terminator tacked onto the end. strcpy does work and does allocate does tack on a null terminator, but the thing to make sure of is that the string you're copying from is small enough to fit in your allocated space. So if you're copying a name from your input to your struct, if the user can specify however long a character he wants, or however long a string he wants to for a process name, and if he supplies something that's 35 characters long, and you have enough space to hold something that's 20, and you try to do strcpy, well, strcpy just says, all right, whatever, and it'll march over the end of your array, and you'll overwrite your event period, you'll overwrite maybe your context, you'll overwrite all kinds of good stuff. This is a buffer overflow problem. That'd be a fun final exam question. How can you make a buffer overflow problem occur on your C-Lab 8? Yeah, I thought about putting a security-oriented twist on this class and say, okay, the last lab is you've got to hook your board up to somebody else's board, and whoever can hack the other one's board first wins. If you can make their board blink LEDs before they make your board blink LEDs, then you win. We'll have a little tournament to see who wins. Anyway.
There's a question.
Yeah, we already commented on what Jonathan's saying. Other questions? Other bugs?
We'll have a printf statement somewhere, and then all of a sudden a working swapping out process will just die randomly.
Okay. Sometimes putting in a printf can cause things to do weird things. Sometimes where you are marching a printf through your code and you finally find where the bug is, and you know that if I just print out this variable, I'll figure out exactly where the bug is, and all of a sudden you put the printout in there and it starts to work.
Yeah.
Or you put a printf in some random location and nothing works now. Check your FIFO to make sure you're not dereferencing garbage pointers, even if it has nothing to do with the printout. So that is probably dereferencing a garbage pointer. And they're hard to find, and sometimes you can use a printf in the control flow to figure out where it's crashing, and you can mark the printf through to figure out where it's crashing, and that'll tell you. Sometimes it has nothing to do with it. But it's just probably a pointer bug on that one. Let's see. The other thing it could possibly be is a timing error, where just the timing of the interaction of processes, by putting a printf in there, we know how much a printf perturbs things. And if you put a printf inside your process and your process has a huge period or a very small period, could putting a printf in there cause it to miss a deadline? Or just putting a printf inside your scheduler all of a sudden makes your context or your pit time become very large. So that could be another thing that causes it. I would also advise you to put a big massive printf right at the beginning of main before you do anything else. Printf a whole bunch of garbage, because what that'll do is it'll cause printf to call malloc to allocate its internal buffers. And so you want those buffers to be allocated before you start running the rest of your code. Okay? So just put a printf, hello world, printing blah blah blah, yada yada yada. I love this class. This is the best class I've ever had. Put that right at the beginning of your code. This lab is too easy, Dr. Eames. Please make some more stuff on it. I'm bored. Okay. More? trigger finger of the pen name. No, okay. Okay, good. Any other comments we want to make? I can barrel on into finishing off the Lab 9 discussion if you want to. We don't have much more to talk about with Lab 9. Then we've got to do EDF and fixed priority, the difference between EDF and fixed priority scheduling. And I got to figure out what else to lecture on. Okay. Yeah, there'll be plenty of Lab 9 questions. Okay, so context switch your poor brains into talking about Lab 9. If you remember, we're implementing a software UART. We're using the input pin and the output pin on the DIO header of the board to interact with a PC or to interact with somebody talking via RS-232. So you got 2 pins on the DIO header. One you're going to use as a transmit pin that will send data out. One we'll use as a receive pin that will receive data coming in. Those pins can take on 2 different logic levels, 2 different voltage levels, voltage 0 and 3.3 volts. We will be using a level shifter chip to take those voltage levels and invert them and convert them into RS-232 levels. So what we'll be doing is asserting a value on a pin, and that value will be transmitted to a PC that's running a serial port. And if you are doing the things on the PC side appropriately, you will be able to send a sequence of bits from your TS7200, and those bits will end up appearing on your PC. Okay? And likewise, you can send data from your PC, send it down to your TS7200, and you should be able to grab that value that you got sent down from your PC, and that you should be able to transmit that in both directions. Okay. So the question that what I want to do is just briefly talk about how do you build this thing. I titled this, How Do You Test Your Implementation? But really what I'm giving you is a step-by-step, this is what you should go through. These are the steps you should follow when implementing Lab 9. Okay? There's a lot of setup, and I'll show you the big grandiose setup at the end of these notes here. But the first thing that I want you to do when you're doing Lab 9 is you should take your board, you should put a wire on your transmit pin, your output pin on your DIO header, and hook a scope to it. Don't hook it up to a PC, don't hook it up to your level shifter, just hook a scope up to it. And then use your board to output 55, or output AA. So this is very similar to stuff that we've already done in Lab 4. So what you're doing is you're just outputting, by outputting a 55, if you have your software in your board, your transmitter software working correctly, and you output the byte 0x55, what that should do is give you a square wave, or an AA. So you're going to have to go through and figure out which one of these should give you the square wave. But if you remember, you're going to have a start bit, and then you're going to have 8 data bits, and then a stop bit, then a start bit, 8 data bits, and then a stop bit. Okay? This guy is a sequence of 0 and 1s, alternating 0 and 1. So is AA. It's a sequence of 0 1s. Just which one has the first bit, the LSB is a 0. The other one has an LSB of a 1. So I want you to go through and figure out which one of these is going to give you a square wave and why. And you should be able to see the square wave on the scope. And at this point, because you just have a wire connected to your DIO, you should be able to see that transmitting. You should see the transmission of a start bit, then the 8 data bits, then a stop bit, then a start bit, 8 data bits, and a stop bit. And if you're doing this correctly, you won't be able to distinguish which one of the voltage levels going low or voltage levels going high, whichever one you're going to end up doing. You won't be able to distinguish your start bit from a data bit because it'll all just be a square wave. If you toggle to the other value that doesn't give you the square wave, you'll be able to see your start bit followed by another thing that'll look like a start bit, and then 8 data bits, then a stop bit followed by something that looks like a stop bit. So, and that's because what you're doing is just offsetting by 1 bit. Your data bits will be out of phase by 1 bit with respect to your start bit and your stop bit. Okay, and then you can try different patterns with here, and you can effectively do pulse width modulation by outputting different bytes with your serial port transmitter. So you can output something that has 1 high and then a bunch of lows and a high, then a bunch of lows and a high and then a bunch of lows, or a low, then a bunch of highs, then a low, then a bunch of highs, and a low, and then a bunch of highs. And you just fiddle around with that until you get comfortable with making sure your transmitter is working correctly. And when you're doing this, when you're testing your transmitter, don't use a context switch. Don't use a process. Throw out all your Lab 8 stuff. Just write a standalone program that just interacts directly with the pin. Okay? You can add in the stuff for making it work with context switching and processes later on. but just do a standalone test program that just implements your transmitter. And again, your transmitter is going to have that code in there that says assert the pin, wait for a particular amount of time, then assert the pin, then wait for a particular amount of time. So you have to iron out how you're going to do your waiting and how you're going to assert your pin. I've given you the code to tell you how to wait and the code to tell you how to assert the pin. So do that. Step number 2, go slow. Not slow as if type of an open brace, then hit a carriage return. I'm not talking about typing slow. I'm talking about slow baud rates. Okay? Use a slow baud rate, fast enough so that the triggering on the scope will still work, but slow enough so that you can discern what's going on. Okay? As soon as you're confident in your transmitter, crank up the baud rate by changing your timer interrupt rate and the rate at which your code is going, and then you should be able to see a corresponding change on the scope. So again, just do a transmitter, fiddle around with the time, make sure you're comfortable with the temporal relationships between the timer interrupt, what you're seeing on the scope, the variables that are being passed, and so forth. Okay? The next thing that you should do is try a loop back. A loop back is where you take your transmitter pin and hook it to your receiver pin. And so what you should do when you're doing the loop back is you again slow it down and then transmit some data out, and during those time periods where you're waiting, then what you should do is pull the input pin. So what you should do is output to your output pin and then check to see if your input pin has the value you just output. You might want to delay just a little bit just to make sure the transients of asserting the pin have passed. So post the value to your output pin, then wait for just a little bit, a fraction of a bit period, and then read your input pin and make sure that those two things match up. So this, again, is just gaining sanity to make sure that you can actually control electrically what's going on outside of your board. So try a loop back. And this is just implementing a polling operation for your input pin. So all of this is just testing your transmitter. Step 4, what you're going to do is separately from your transmitter code, implement receiver code. So again, this is another program that is outside of the context of your operating system. No processes, no context switching, no semaphores. You're just going to implement a standalone program that does receiving. Similarly, we're just receiving on the DIO pin. You're not using your level shifter chip yet. So you implement your receiver, and what you're going to send to your receiver, you're going to hook it up to your square wave generator from your function generator. Okay? So you'll configure your function generator, and again, be careful on your function generator to dial in the DC offset and the amplitude so that you get a 0 to 3.3 range on your square wave that your function generator is outputting. Don't blow the board. Don't let the smoke out. Bad. Okay. So implement the receiver, have your function generator output a square wave, and then see if you can appropriately receive the square wave that gets generated. So you can start this by doing a similar operation to what you did in step 3 by polling the input pin and seeing what values you get. But then you go through the process of formally implementing your receiver by sampling and then waiting and then sampling and then waiting and then sampling and then waiting and detecting when you get a start bit. And as soon as you get a start bit, then you wait for a bit period, get the next data bit, next data bit, next data bit, next data bit. You implement your software shift register and you collect all the bits into the first data bit, and then you see what the byte is that resulted, and you print that to the screen. Okay? So this is the operation that you're doing for implementing the receiver. And once you have some confidence that your receiver is working, then you go on to the next step. So in step 5, this is where you put both of your receiver and your transmitter together and you implement a loop back. Okay? So you hook your output pin to your input pin, and then you run your transmitter and you say, I want to transmit 0x55. And then at the same time, you're running your receiver. And again, this is your transmitter and your receiver running concurrently. So you're going to have to figure out how to resolve that concurrency issue. And then you're going to just check to make sure that you're receiving what you're transmitting. And then you're going to change a few values that you're going to send out your transmitter and make sure that you receive all the values that you transmitted. The next thing is now you use your level shifter chip. So all that the level shifter chip is it's just going to change the logic level. So you're going to hook your transmitter up to a transmitter, to the transmitter side of your level shifter chip. you're going to hook your receiver up to the receiver side of the level shifter chip, and then you're going to hook up your transmitter output to your receiver input. You'll put a scope on that wire that hooks the transmitter output to the receiver input. So you should be able to see now, instead of 0 to 3.3 volt square waves, you should see plus and minus 7 volt square waves. But your loopback connection should still work right. All that we're doing is, instead of just having a wire hook your input pin to your output pin, we're having a wire go to the level shifter, and that'll do an inversion, then throw another wire to the other part of the level shifter, and then that level shifter will go to your input pin. So we're just putting a level shifter in the mix. And so that'll just be looping back by converting the voltage levels to RS-232 level and then back again, and then send that back to your board for more testing. Okay? Then, as soon as you've got that working, now you're ready to talk to a PC. So you forget your receiver for a bit, you do your transmitter with a level shifter. So you're going to send data output through your transmitter, through the RS-232 level shifter chip, send that through an RS-232 cable, and hook it up to a PC's RS-232 port. This will probably require you to hack a cable. Do not cut the cables that come with the boards. I have got cables you can hack. Okay? So if you want to hack a cable, then what I mean by hack a cable is physically take a knife and chop the cable up and get the wires that are inside it. I've got cables you can cut apart. Okay? So come and ask for one if you want one. So on the host side, you'll have to hack the FLD code to properly receive data and print to the screen of what was transmitted. So you've got software inside FLD which will interact with the serial port. You'll open up the serial port. You'll have to configure the serial port to hit the right baud rate on the PC side so that both of those guys agree. You do the same thing for a receiver when you're testing your receiver, and then you can do a full duplex infrastructure. This is what your test is going to end up looking like. You have a TS7200 that hooks with your normal serial cable up to your PC. This PC is what's going to receive your debugging prints. Okay? This PC will load your program. You'll run FLD here and run your program down to your TS7200. Your TS7200 on your DIO header will connect to your breadboard with your level shifter chip on it. So you'll have multiple wires here, one for transmitter, one for receiver going to here, and also ground and power. Then here, your level shifter will have your hacked serial cable to another PC, and this other PC will have a serial port. And this is the PC that will be running your hacked version of FLD, where you'll be sending data down to your TS7200 and getting data back. Okay? So you'll have two PCs here, one for debugging stuff, one for your printfs, and this one for your interacting with your board on your serial port. Okay, that's Lab 9. Do it in slow, simple steps.
Yeah, I got it. Yeah. Yeah.